Hey guys, welcome back to this week's video. I'm Melina, and today we're going to be talking about electrophilic aromatic substitution. So, what is electrophilic aromatic substitution? Basically, you have a aromatic ring that's acting as a nucleophile, and on that aromatic ring, you're going to have a aromatic hydrogen. Excuse me. So what happens is this is going to react with an electrophile, and the aromatic hydrogen gets switched out. It gets substituted out with an electrophile. So let's go a little bit more into the mechanism. So the first step that happens is the pi bond is going to nucleophilic attack the electrophile. And what forms is the sigma complex, where you have a carbocation right here and a carbon that is attached to an aromatic hydrogen as well as the electrophile. The next step that happens is a proton transfer, where a base comes in and grabs this hydrogen. And the bond between the carbon and the hydrogen is going to form a double bond again, so the structure can reform its aromaticity. And that's what's depicted right here. The same aromatic ring, but instead of a hydrogen, it now has an electrophile. So let's look, these are a couple of the electrophilic aromatic substitution reactions you need to know. You guys do need to know mechanism, but don't be afraid. They're all the basic mechanism as depicted here, that's with different reagents and different electrophiles. So you have halogenation, which includes bromination, chlorination, and iodination, nitration, sulfonation, Friedel-Crafts, alkylation. Remember, with this reaction, alkylation, you always want to form the most stable product. So if you can form tertiary, try to form tertiary. And lastly, Friedel-Crafts acylation. So when doing these electrophilic aromatic substitution reactions, we also have to take into account directing groups. So what are directing groups? Directing groups are substituents that are already on the aromatic ring that can affect where the substitution occurs. It's going to affect what type of product is formed. So we have two types, which are electron donating groups, known as EDGs, which donate electron density to the aromatic ring and are activating. And we have electron withdrawing groups, also known as EWGs, which take away electron density from the aromatic ring, so therefore they're deactivating. So let's go a little bit more in depth. So electron donating groups donate electron density to the ortho and pair positions. So that makes the ortho and pair positions more reactive. The pair position is going to be the major product, and the ortho position is going to be the minor product. So let's look at an example. OH is an example of an EDG, and it has a lone pair here that's going to move in and form a double bond, which is going to kick this double bond up into a lone pair onto this carbon, which is depicted right here. And so, as you can see, as a result, by the oxygen moving its lone pair to form a double bond, and this bond had to go up to form a lone pair, this is the ortho position. And this ortho position now has more electron density, making it more reactive. And if you do the same thing, go through with the resonance, push this down to make another pi bond, and push this pi bond up to form another lone pair. This is now the pair position, which has more electron density, so is therefore more reactive. And you go again, and it would form another lone pair on the other ortho position. Now, let's look at an example with an actual reaction. So we have an OH here. If you go through with this is the nitration reaction. You can see that you would get the NO2 group added onto the pair position as well as the ortho position. But remember that the major product is going to be the pair substituted product. Now we have electron withdrawing groups. These take away electron density from the ortho and pair positions. So by default, this leaves the meta positions more reactive because the meta positions are not being touched. So let's look at an example. So this group right here is an EWG, and this pi bond can move its electrons to this substituent, and these will go up. See, it's taking the electrons away from the aromatic ring, which results in a carbocation right here. And if you continue with the resonance and move this pi bond over here, the next carbocation results at the pair position. And you go again, and it would result in a carbocation at the other ortho position. So because the ortho and pair positions are more positive, they have less electron density. And as a result, you can see that the meta positions right here, they're untouched. Their electron density remains the same, but because it's remaining the same compared to the ortho and para positions that have theirs taken away, the meta position has more electron density. So that's why the meta position is more reactive. So if you have if you have an aromatic ring with an electron withdrawing group on it, the reaction is going to go through and result in the meta-substituted product. So let's look at another example with an EWG. So notice that I put the EWG right here as opposed to right here. This is just a reminder to show you guys that ortho, para, meta, these are all relative. It doesn't mean that ortho is always going to be right here. It doesn't mean that meta is always going to be right here. And it doesn't mean that para is always going to be right here. You have to look at these in respect to the directing group that's already on the benzene ring. So this is an EWG going through with bromination, and it would result in a bromine added onto the meta position. So it could occur here or here, doesn't matter as long as it's meta. Lastly, we have halogens. So halogens are electron withdrawing groups due to the inductive effect. But remember that halogens also have lone pairs that can contribute to resonance within the aromatic ring. So because of that, like we've seen with EDGs, if you're donating electrons into the ring, it would result in ortho and para being more reactive. So halogens, they are withdrawing groups, but they select for ortho and para substituted products. And just like EDGs, para will be the major product. So this is another example. Here we have halogen, chlorine. Notice I put it on the bottom, just to remind you guys about, it's ortho, para, and meta, it's all relative. So this reaction right here is Friedel-Class alkylation, and this results in this product. It is the para substituted product, and notice that this is the most substituted product. Because if you were to react right here, this would be primary, but you can do a hydride shift and move the hydrogen that's right here to go here to form the tertiary product. And this is the major product, the para substituted one. The minor product would be ortho, but you would not see that just because tert-butyl is so big and bulky and it'd be like next to this halogen, so there would be a lot of sterics. So yeah, guys, that's all for this video. I hope you guys enjoyed watching. Thank you.